Okay, so the second question that I'm interested in us examining is this idea. I'm giving you a line and I'm asking you if these other lines are parallel, perpendicular, or neither. So I'll give you a second to copy this down. As you do that, we'll just talk about how we determine if things are parallel, perpendicular, or neither. So of course the trick in these questions is the form of the equation that I'm giving you is different, so you have to work your magic to figure out the information that's necessary in order to decide if the lines are parallel, perpendicular, and neither. So the first one you'll notice is L1, and it's x minus 1, y plus 3, and z is equal to k, bracket 3, negative 2, 1. So of course, in order to compare this line to all the other lines in the other questions, we need to compare the direction vector, because the direction vector, of course, gives its direction. And if we find other lines that have same direction vectors or scalar multiples of those direction vectors, then those lines would be parallel. If the direction vectors are perpendicular, then obviously the lines are perpendicular. And if they're neither, then neither. So the first thing I need to do is identify the direction vector of L1. So of course in this form, we see the direction vectors right there. So I'm going to call it D1 for the direction vector of line 1 is 3, negative 2, 1. And we're going to use that to compare it to the direction vector of all the other lines. So in A, we've got line 2, which is negative 4 minus x over 6 equals y over 4 equals 1 minus z over 2. So we look at it and we see it is the symmetric equation. But the only catch is, remember, we can't just read off the direction numbers from the bottom. It has to be in the correct form. This one's definitely not in the correct form. You see up here you've got your x in the wrong spot, and this one the z's in the wrong spot. So we have to rearrange things. We can do that by multiplying everything by negative 1. So the negative 4 becomes a plus 4. The negative x becomes a plus x, and we can put it in the front. However, the bottom is going to be minus 6. The y over 4, it's okay. It's in the correct form. The z is in the wrong spot. Again, multiplying everything by negative 1. So the minus z becomes a plus z, so I can put it first. The plus 1 becomes minus 1, and on the bottom be negative 2. So this equation I wrote in blue is in symmetric form, but it's not in the form we like it. Remember, one of the rules of symmetric is put all the negatives on top. But in order to read the direction vector, we need it in the correct notation. So here it is in the correct notation. We now can quickly read the direction vector is at the bottom. So this is D2 is now negative 6, 4, negative 2. Now we have to compare that to our green direction vector. And at first glance, you might say, hey, they're not the same. But at closer examination, you realize that if you take D1 and you multiply it by 2, you get the right numbers. Then you see if you multiply by negative 2, you get negative 6, positive 4, negative 2. And so D1 and D2 are scalar multiples. D2 is just negative 2 times D1, i.e. they are scalar multiples. So that means that these two lines have direction vectors that are scalar multiples of each other, which means they are in the same direction. Just one's bigger than the other, no big deal. Or at least lie on the same line. And so they must be parallel. So L1 is parallel to L2. So you see why these questions are interesting, because we have to get the information from the question, so you might need to do a little bit of work to find the direction vector. Once you get the direction vector, you make a comparison to the original, and that will tell you if it's parallel or perpendicular or maybe nothing. So in B, we're looking at L3, so a different line. This has got, in a different notation, it's x, y, z equals 3, 0, 1 plus t, -3, -2, -1. So there isn't a lot of work necessary in this one to figure out the direction vector. So this is D3. Direction vector is right there. -3, -2, -1. So at glance, again, you might get excited that it is parallel because you see the 3, the 2, and the 1. But at careful examination, you see it's a little bit different. The 3 is a -3, so that's still okay. So I could multiply everything by -1, but you see it doesn't hold true here. You know, it breaks down right here. And so that means that D1 and D3 are not scalar multiples. How can I write that? So D1 is not a scalar, or D3 is not a scalar multiple of D1. So it's not scalar multiples. Now, that doesn't mean that the answer is neither. Scalar, it just means that it's not parallel. The other option is it could be perpendicular. So I've got this, and I've got to figure out, well, how could I tell if D3 is perpendicular to D1? So I'm hoping someone will be screaming at the board that they know how to tell if D3 is perpendicular to D1. And being that you are the best class ever, you of course will not forget this. You will remember that to figure out if these are perpendicular, we will take their dot product. And if the dot product is 0, we know they're going to be parallel, or sorry, perpendicular. So we can quickly do a dot product. We'll just do it right here. We multiply the x's, the y's, and the z's. It doesn't matter if I'm doing d3 dot d1 or d1 dot d3. It doesn't matter. So you multiply, and I'm going to get -9. Oops. -9 plus 2 plus -1. And that, of course, oh, sorry, not plus 2, plus 4 -1. And that, of course, is equal to, well, what, -6? I mean, frankly, I really don't care that it's what it is. I just care that it's not equal to 0. So since their dot product is not equal to 0, then it's not perpendicular. So therefore, these are neither parallel nor perpendicular. So I've got a third example, and I'm sure by process of elimination you could figure out what this one's going to be, but let's check. So in this is third example, again, it's in a different form. This one's in parametric. We have to get the direction vector. The direction vector in this case will be the coefficients on the r. So the direction vector of 4 is -1 is the coefficient there. There is no r here, that means it must be a 0. And this is a 3. So there's our direction vector. We're comparing it to the direction vector up here at the top, the green one. So I'll just recopy it down here so I can see it. So D1 is 3, -2, 1. And this one you can actually, if you remember the shortcut, you can confirm here. Remember, one way to get a perpendicular vector is to take two of the components, change them, make one of them negative and the third one 0. That's what happened here. You see the 3 goes to the end, and the 3 here goes to the end. The 1 goes to the front and is negative, and then this one becomes 0. So I know that it's perpendicular. But I should do the little test off to the side just to be safe. So let's do d4.d1. So this will be multiply the x's, we get -3. Oops, don't need the bracket there. So it'll be -3 plus 0 plus 3. And of course that's 0. So therefore they're perpendicular, and I can then assume that L4 is perpendicular to L1. So another cool question, because it really gets us to go through and study all of the things we know about direction vectors, take the equations and lines, come up with direction vectors so that you compare whether they're parallel, perpendicular, or neither.